Here's another example of recursion. Assume that multiplication is cheap here and that it doesn't mind the numbers getting big. But here the input is a B and a capital N, and we need to compute B to the capital N. So how do you do it? Well, one option is to, the base case when n is 0, the answer is 1. Otherwise, you take n divided by 2 and round down and then compute that answer, and you round up and you recurse on that answer, and then you multiply them. So here's an example. If n 7, then we recurse on 3 and 4, and they give us b to the 3 and b to the 4, and we multiply them together to get b to the 7. Right? Everybody got that? Yeah. Is this a good algorithm? Why not?
It's very high complexity. Yeah.
Yes. All right. So it works, but if we see what is happening, it's spanning the whole tree out of, and it's going to have capital N base cases, and you can sort of play with the recurrence relation to see that the running time will be capital N. And as we know, the size of the input is only log n, so this is exponential in the size of the input. Everybody got that?
No, I don't got that. Have to do it again?
Do you get that the running time is capital N?
Yeah.
Right, because it keeps, in fact, I said this at least once, maybe not here, is that if I have a certain amount of work, and all I do is I give that work to various people, and I don't destroy any work, then conservation of work, the work doesn't go away, right? So I have to do, if I want to do B times B times B, capital N times, I want to do capital N multiplications, then all I'm doing is giving that work to other people, right? So it hasn't really gone away. I guess the multiplication between the pieces, I give this piece, they do those, and this piece does those, and I do the one that puts them together. No multiplication has been destroyed, right? So the only way we can have a savings in time is if we somehow get rid of some work.
So how do you know it's big data and
Well, one, you could solve this recurrence relation using the log A, log B method,
yeah.
Or you could trace it out and see it, or you could see that no works are destroyed. All right? Should we do the log A, log B method? Do people know how to do that?
Not really.
So the top work, right? How much work am I personally doing? I'm doing n to the 0, right, which is 1. So C is 1. And then log A over log B is what? What's A? A is 2. Right? What's B? B is 2. So log A over log B is 1. C, oh, you're right. I had that up there. Exactly. C is 0. And which one's bigger? This one's bigger. Right? So it's dominated by this. And so the running time is n to the 1. Except it's a capital N. Right? Everybody buy that? What don't you buy?
Oh, okay, why is that capital N there?
Because the running time is either the work at the top, or it's into the log A over log B, depending on which one's bigger. Right? This is the F to the N is n to the C. And so we see which of these is bigger, and we say it's dominated by the base cases. This is the number of base cases. All right, everybody following that? right? And you can see sort of here that the number of base cases is capital N, right?
Yeah. The Y, okay. That's the little one. Have you turned that little one into capital?
Everything on here should be a capital N.
Oh, okay.
All right? And now the little n is the size, right? The little n is the log of the capital N. And so this running time is 2 to the little n, right? Exponential in the number of bits to write it down. Yeah?
Is it ever possible to have a capital N and have it not be exponential?
If you divide in, yes, wait till the next slide.
Okay.
All right, everybody ready for the next slide? Oop. Few simple steps, everybody. All right, so sorry about that. I don't know how you guys all manage your phone. I never quite managed my phone. All right.
I just turned capital N to the end.
Capital N is the number of bits to write down the input,
Oh, okay.
and the number of bits, so little n is log capital N.
Okay, and input in this case being what?
Little n is log capital N, so capital N is 2 to the little n.
And the input is just B and M?
Yeah, well, here I got the number of bits in B, but we can assume B is something small.
Okay.
All right, and this is actually something. So in practice, here the size of the output is going to grow and grow and grow. So in practice, this is done mod some prime number, and it's something that actually is very useful for cryptography and stuff. But we're not getting into cryptography right now, so we won't worry about it. All right, so now how can we do, anybody see how we can do a savings? We have to decrease the number of friends, right? Why did we have 2 friends here doing basically the same work, right? So instead, we divide in by 2 and round down. We have 1 friend that computes it, and then we square it, and when it's odd, right? So here's our n. We have 1 friend who gets 3, and so we get, a friend gives us b to the 3, and we square it and bring in an extra b because it's odd. Right? Everybody buy that? Right? And how does that change the running time? Right? Now we have 1 friend. So this is a 1, which gives us a 0. Right? And so how many, we have to calculate both the running time and right? So let's go through here and see what the running time is. What's the running time then going to be? Right? Here, C is 0, and log A over log B is 0. Right? So they're equal. So then the running time is what? Well, it's just log n. Right? I mean, how many base cases do we have? We have n to the 0, which equals 1 base case. And why do we have 1 base case? Well, I have 1 friend, he has 1 friend, she has 1 friend. There's only 1 at every level. Right? So the work at every level is 1. And they're log n levels. Yeah?
So conceptually, you're passing half the input to the person below you. They're multiplying it by, they're doing their job of multiplying it and returning it back to you. And you're also multiplying and returning it back.
You're squaring it and returning it back.
Okay.
Yeah. Right? So see here, right, the number of levels is log n. Yeah?
The percent of comment, like in your pseudocode, is that percentage sign a comment?
Yeah. I don't know. I'm old school. I always use percentages for comments.
Okay.
I don't know what programming language that is. But
very distracting to look at because I keep thinking it's a modulus. Yeah.
All right, fair enough. Fair enough. Any other questions about it? Right, and so then, you see now we have that the number of multiplications is the same as the number of bits, not the value. Right, everybody see the savings there? Yeah?
Can you say one more time, the last sentence? Number of
Yeah, so the running time is order log capital N, and the size is order log capital N. So the time is proportional to this number of bits, right? So we can say linear. This is linear time. If we count multiplications as constant time, then it's linear time, which means the time to look at the bits of N, right? N stored as bits. How long does it take you to look at the bits? It's the same as the amount of time to solve this problem, right? And you can't do better than that because surely you have to look at the bits to answer the question,
Okay.
right? So linear time means, right, the time to do it is the same as the number of time to look at the bits. All right, any questions?